All right, just a quick tidbits. So I went ahead and started uploading all these videos to YouTube. I'm gonna delete them from the Google Drive because they just take up a ton of space. So just kind of just be aware. I'll put them all in the playlist on YouTube, and I'll share the link when that's all together. A lot of them, I think I added the past three already, so they've already been uploaded. So there you are as well. I'll try to annotate them as well, kind of adding links to the pictures I've been taking. Because if you just look at the screencast, all the information on the board is reflected, so that's a little awkward. So I'll add some pictures with everything as well. So I guess I have a quick review. We're kind of doing this bioinstrumentation workshop. The point of it is, depending on what grade level you are, is to kind of introduce people to circuits, particularly those who haven't taken 301 and 305 yet. For those of you who have, it's kind of giving you a little bit of some extra application practice, and there's certain things we may not have done in 305 or 301. So some of that has quite a bit of, I would like it to have a sort of a design component. So I have asked everyone to sort of think of a thing that they'd like to build during the workshop, and so we can power through that as we go. So I'll actually, in a second there, I'll kind of ask you guys what you had in mind. And so the idea of the workshop is that we're going through analog circuit design. So not really digital, so building things at time varying signals. So that includes using filters and amplifiers, and then processing it in some way using a microcontroller. So far, we've kind of done a lot of the basics. Just kind of get people who haven't taken 301 and 305 up to speed. We started off doing some basics, intro to electricity, Ohm's law, current, voltage, that type of things. And then moving into microcontrollers, just the basic of using microcontrollers. So our platform for the workshop is going to be Arduino, because it's really, really easy to use and simple, particularly for beginners. So that's really, really helpful. So we did a couple of things there. We did kind of the, I don't want to use the word stereotypical, but just the typical intro stuff, fade, blink. So we talked about the difference between digital and analog. Then we talked about what's pulse width modulation, analog read. Then we introduced a couple other things that usually don't get discussed, at least not in intro Arduino stuff. In particular, interrupts. So hardware interrupts. So looking at sudden changes in pin state, and then actuating some small piece of code based on that change in pin state. We also kind of gleaned over timer interrupts. I didn't really structure that lesson too well, so it seems like everyone was somewhat disconnected and it wasn't really flowing well enough. So timer interrupts, instead of looking at changes in pin state, it just keeps it does a certain bit of instruction at a very specific interval of time. And that's really, really good for sampling, so that you have a very, very consistent sampling. So the point of this workshop is to frame around basics of circuit design and then use it to do some sort of fun project. So right now we're talking about amplifiers. So amplifiers, or op-amps, are basically these little components that can do mathematical operations on signals. For those of you who are in 305 and 301 or have taken them already, you should be fairly well caught up with those. For those of you who haven't, hopefully this is a really, really good introduction, and they're helping you kind of understand those things. Although for analog circuit design, op-amps are pretty ubiquitous, just kind of get used to manipulating them. And so we're going to go from that, learning from the basics of op-amps. We started last week just basically doing DC analysis, so there's no change in voltage. So we just took your voltage dividers, a light-dependent resistor. In your case, Damon, you took a photodiode and a transimpedance amplifier, and you looked at the change in output voltage with changing amount of ambient light. For those of you who were present, the ones who did this last week aren't present, but essentially we basically built a basic night light. So we took a photoresistor, a couple voltage dividers, and a comparator. And so in the photoresistor, sensed that it got dark, the comparator changed states to high, so it turned on the LED. When it was too bright, the photosensor noticed that the ambient light was high, and the comparator changed to low, which turned off the LED. So that's the basic kind of actuation mechanism for a simple night light. So today we're going to start doing some time-varying projects, so introducing capacitors and what those are and how important those are for different things. And so we're going to do probably one of my personal favorite projects is LED Blink, but this time was simply just op-amps only. For those of you who came to Fun Times last semester, I probably used this a couple times already. It's called an Astable multivibrator circuit. So essentially it uses positive feedback, not just negative feedback, and hysteresis to change the state between the op-amp's output automatically once it's powered. And that's actually pretty neat. And so what we're going to do with that, what I'm trying to do as well is to integrate all different lessons so that you're not just learning these random tidbits of things, but you have to incorporate them into small mini projects. So what I'll have you do is to use this Astable multivibrator to actually have a microcontroller read the output and then do something as a result. And so we'll kind of get into that right about now. Sounds good? Any questions so far?
I'm just installing the library.
Oh, you're fine. Any questions, Damon? So I'm pretty sure I had some capacitors on that DigiKey list, right?
Yeah.
Maybe 10 microfarads or 1 microfarad, something like that. I forget which specific values, but I'll kind of let you dig through that here in a sec. I don't quite have a PowerPoint prepared for today, so I'll just use Google Images to go over things. So capacitors are another one of those ubiquitous circuit components. These are time-dependent signals. These are time-dependent components, so we can use them. We can actually use them to create filters. And I'll show you what that means, through simulation. I kind of planned on just using a simulator today, although with the Google Hangouts feed as well as the screencast, this might run a lot slower than I anticipated. But we'll see how this works. I might just have to draw this on the board a lot. So essentially, with resistors, resistors are not time varying. So when a voltage is applied to the resistor, the current is also applied instantaneously. But with a capacitor, though, the current actually leads the voltage. Ooh, am I saying that right? Ooh, I might need to check that for the record. This leads to a positive phase. The phase is negative for a capacitor since the current leads the voltage, as opposed to in an inductor, the current actually lags the voltage. So what that means is, just kind of boiling it down, it takes a time for a capacitor to charge up to a certain voltage when a current is applied to it. And I'll show you what that means, more or less via simulation. Microseconds. So if I have a capacitor and resistor in series like so, it actually creates a low-pass filter. So that means is if I have a time-varying signal like a sinusoid, it takes a while for this capacitor to charge up such that it actually blocks certain frequencies from passing altogether. So if I have this sort of time domain simulation, and what you'll see is, though I have a DC current source, this is not working wonderfully, unfortunately. Let's do this way. One second, guys. 100 ohms, 1 microfarad. That should be a time constant of 100 microseconds. Oh, my time step was way too high. With 100 kilo ohms. So I need it to be on the order of 2 seconds. That's a little bit better. Okay, this is a little bit better. All right, Damon, are you seeing this? So you can see here is I'm applying a, actually, I'll add another voltage here. I'm applying a square wave voltage to the circuit, as you can see in orange, but the voltage across the capacitor is not changing, completely in phase with the input signal. And that's because current leads the voltage, so that means the voltage is actually lagging behind the input current here, which is our square wave. And so what that happens is, if I increase the frequency of the signal, because the capacitor is operating so slowly, so I'll increase it to 10 hertz, so 10 cycles per second. You can see that the capacitor stops charging up to that full voltage the faster this wave gets. Wow. It's gonna be that kind of day, unfortunately. Yikes. Then in this case, it actually starts charge, so it doesn't discharge in this case. Let me do something else. Skip initial stuff. Yes. All right. So in this case, it's not even charging up barely to half the voltage like it was before. So if I decrease the speed of the wave, it will slowly climb all the way up to half dB. Well, actually, not necessarily. So it doesn't necessarily charge up to the cycle as fast as the input square changes, but it should actually charge up to half, or to the average signal. But it'll just take a while to do that. So you can see as I decrease the speed of the wave, going from 100 hertz to 10, and now back to 1. You can see that the voltage across the capacitor is resembling the input voltage a lot better the slower the signal gets. So this is called a low pass filter. So it only allows really, really slow signals to pass. And what we can do is we can figure out, what's that cutoff. If it's anything higher than this frequency, the signals won't pass. If it's anything lower than this frequency, the signals will pass. And we can do that with a very simple equation, which is 1 over 2 pi. So 3.1, I should put in pi, times the resistor value, which in our case was 10 kilo ohms, I think, times 10 microfarads. And so that tells us the cutoff frequency of our signal. So ideally, what that means is, if the signals are any faster than 1.59 hertz, they won't pass through our filter. If the signals are slower than 1.59 hertz, they will pass through our filter. Is that kind of making sense, Damon? All right. And so we can utilize this sort of, charging action of the capacitor to our advantage in some ways. And so with the circuit I'll actually have you guys build today, the Astable Multivibrator will be doing exactly that. I don't know what my username is. No idea why the password is. Maybe it's going to go for it. Alright, so I need to call it Team Valor Wired Up Badge Pokemon Go. And so this is something I built, I think, probably either last summer or 2 summers ago. I forget when Pokemon Go came out. But essentially, I created this little Astable multivibrator circuit, and I attached it to an LED. And I was able to get this action. So this is because the capacitor takes a while to charge and discharge. So essentially, we get a blinking action with the LED. Square wave oscillator. And so this is a quick image of the circuit. I'll more or less kind of give you an overview. Right now, it's somewhat dense, but essentially, we have 3 resistors and a capacitor. So this resistor and this capacitor here create this low-pass filter I was telling you about, and so these 2 resistors here create a bias network. So what happens is, if the voltage at the output is, let's say, high, or let's say 5 volts, it will charge this capacitor, and it wants to charge it up to 5 volts. But last week we talked about comparators. So what happens is that the voltage at the V minus input, now I'll actually write comparators on the board real quick so we can review. So last week we talked about comparators. Plus, minus, and if they have some power supply, let's say VSS, VSS, VDD. And so what we said is V out is equal to 10,000 times the difference between V in plus and V in minus. And then we also said V out is less than or equal to VDD, greater than or equal to VSS. Does that ring a bell, Damon? Yeah. So essentially, if V in plus is bigger than V in minus, the output is VDD. If V in plus is smaller than V in minus, the output is VSS. And so this is hypothetically 5 volts, and this is hypothetically 0 volts. And we switch between the 2 states. When it's 5 volts, it'll turn on the LED. When it's 0 volts, it'll turn the LED off. Let me take a picture of this. And so, if we have our square wave oscillator, and I'll make a couple changes now. We'll actually connect these to 1/2 VDD, and we'll power our amplifier with ground and with 5 volts. And these are the MCP 6002s. And so how this guy works is, let's imagine that this starts off as high. Let's imagine that it starts off as 5 volts, the output. And so then we'll have current flowing through this resistor and then to this capacitor, so that it's charging the voltage across the capacitor. And so the VC will increase, and such that it will get close to 5 volts. But at the same time, we have this resistor network here. Let's say they're the same, they're equal. And so because they're equal, the voltage here is going to be 1/2 VDD or 2.5 volts. And that goes back to our voltage divider equation when I showed this a couple weeks ago. And I said V out is equal to V in times R2 over R2 plus R1. And so based on that equation, if the two R's are equal, V out is equal to half V in. Good so far? I know you just caught it. So in the case of our square wave oscillator, if these R's are the same, then this voltage here, which is the same as this voltage, is half this voltage, more or less. It's going to be in between this and this, so probably somewhere on the order of, I don't know, 375. The exact number isn't all that important. Is that making sense so far? Okay, cool. And so what happens is, if V plus is greater than V minus, we said a second ago with our comparator, then the output is high. But as VC, the voltage across the capacitor, increases, as soon as it gets above 3.75, then V in minus is going to be greater than V in plus, and then the output is actually going to go low. And then when that happens, this is now 0, and this is still 1/2 VDD. So this number is going to be, the exact number isn't a big deal. It's going to be like 1.25 or something like that. And then this action starts all over again. So now the capacitor starts to discharge. And the voltage across the capacitor drops. So now it was 3.75, or some number between 2.5 and 5, and now it's going to start to drop. And then as it drops, if it drops below 1.25, then V in plus is going to be bigger than V in minus again, and so our output's going to go back high. And then this is a continuously repeated action. Does that make sense, Damon?
Yeah.
All right, so I know you've seen this before. Scott, you following? Got it. Following? Got it. Any questions so far? That's a very broad question. I mean, it was more of just a review, and we talked about capacitors needing to charge and discharge. So what we're going to do is we're going to make an Astable multivibrator circuit. I think that's just the name it goes by. Astable. Or a square wave oscillator, so astable because it's not stable in any state. It keeps switching between high and low. Or a square wave oscillator because the output basically looks like a square wave. So we're going to use the whole capacitor's charge and discharge idea to our advantage. So essentially, when this circuit goes to high, it charges the capacitor. When the capacitor voltage reaches a voltage higher than V in plus, because this is a comparator, it's going to switch the states. Because if V in minus is bigger than V in plus, the output is ground. And so then the capacitor is going to discharge, and so when it discharges, eventually it's going to drop below the voltage of V in plus. So that means V in plus is going to be bigger than V in minus, and based on our comparator equation, that means the output is high. So it's going to switch back high. And then it's going to repeat the cycle over and over again. Does that make sense? Kind of? Okay. So this is the bias network, so this sets the voltage at this pin.
Oh.
And so this guy here sets how fast that whole switching action occurs, because that's your filter. So it might help for you guys to see it real quick. So to see it real quick, and then we kind of talk about it again. So I'll just send you off to do the circuit, to just build it. I'll share a screen. And I'll just put this link in the group chat. So this, you can just scroll down to the circuit step. It should have everything laid out with all the right values. Damon, use whatever you have that's just close to these values, and you should be okay. And if you have any questions, let me know, and we'll just kind of reconvene after you guys think you have some part of it working, or if you have any questions. Come on, I might have to do this on my computer, from my phone. Almost there, almost there. All right, it should be in the group. So just follow the circuit on step 3. So you don't need the transistor. You can just hook the output of this amplifier directly to a resistor in series with an LED. So just kind of follow that for a sec. If you have any questions, let me know. And then after you get it working, we'll just kind of reconvene and talk about it a bit more. Sound good? All right, I'll leave this on this page here. So I'm still doing, okay. All right. Do you guys already have components, or you just have?
No, we just showed it up. It reminded me that we need to order.
We have the
No, I don't have to do it. Yeah, it's not with me. Yeah, sure.
It's not a big deal.
I actually had a question.
No.
Oh, so about bias networks, I noticed like the same type bias network in Pedro circuit for the EMG, but I wasn't quite sure how it works. This guy and I are working on the EMG. Yeah, like how does this bias your input to 1.25? Because this is an infinite impedance terminal, and then that's an AC source.
Does that bias the input to 1.25?
Like I don't understand the point of this section of the circuit. It seems like it's just a path for current to go. Because this is like this.
Not necessarily sure bias to 1.25.
Because, okay, it doesn't bias it, because they have, I think this biases it to 1.25.
So what this happens is that when you connect your electrodes to yourself, there is some DC to it. So if you remember from your electrode like a base model, there's a DC. So
Yeah.
So what that does is when the current flows in DC directly to your electrodes. So this is what goes to the ground. So it keeps it within 1.25 and there's a positive calcium. So like you said, this is a high input impedance to the wind, and this is a low input to this. So the ground in this case is 1.25. So okay, no. So in the case of a regular voltage divider,
Which is like, it's simple, this is just where you take the voltage.
right? So if this is bigger than this, then it's going to be close to your input, right? Right.
I think it's R2. Yeah.
And this is close to, is close to whatever this is. This is the ground.
Yes.
R1.
If R1 is significantly greater.
Then if you replace this,
So it's, okay. I see. So then that's a closed loop. So it's saying if the resistance of the electrode would be this R1 here, that would be 1.25.
Yeah.
And that would be 15 kiloohms.
Yeah, so this is
That's your electrode resistance. Yeah. So what do you think the point of that is?
So it's to keep your so what often happens with these is This is oh, this is a 2-part source, so this has some AC component.
Yeah.
Right.
Yeah.
So if you just stick this into a high input infused amplifier, your amplification, right? You're gonna have both the AC signal and the DC component amplified, right? So the DC component is relatively large and your gain is high. You're gonna saturate your signal.
Yeah.
So if you have it half the ground for the DC component, your DC component isn't okay.
Okay. But doesn't it still form the electrode form the voltage divider with this?
It does, but I think you decided that wife, I'd have to see it. This should be significantly larger than the 15K.
Probably a bit greater. Usually with lead electrodes, I think it's like 60 kilo ohm.
So it should be a bit larger than that 15K. I have to do the simulation.
Okay. Maybe it'll keep it.
If you simulate this,
I can do those right now, actually.
it's like a pitch. Because you have to connect. You connect your ground of your body in that circuit to 1.25 as well, right?
No, I think you connect it to ground, actually.
To the ground?
Yeah. I'm pretty sure it, like, literally like, goes right there to your elbow.
Okay, that's fine. So let's simulate this, but this should be within, the real higher than 1.25 volts.
Okay.
And so if you keep these more or less the same, with the regular network, these subtract. So you don't get any DC.
Oh.
So you're trying to force these to somewhat be close to 1.25, so they subtract that. There are a couple ways to do this. In some cases, you have to put. You actually go ahead and put
Yeah, theoretically, wouldn't they subtract these?
right, but these are not equal. So, like, if you have a EMP electrode, you see one is not equal to DC.
Yeah.
So that you get someone with their arm, and this is the rest of like 6 seconds.
No, that was good.
You go up to
It's pretty neat.
go up to here. Like I said, the signal here is not equal to
Yeah.
those two DC components.
Yeah, because Scott and I are trying to sort of make a better version of this refine.
I mean, what are you trying to do with that?
Well, we're just obviously make it smaller, and then we're making our own electrodes.
So there are like some pre-amplifiers that are ICs
That go on the electrode.
no, but they have all this built in, and they have several channels. So you can get like 16 channels. And all it is basically this built in.
Oh, really?
So you want it smaller, you want a lot of them, right?
Oh, you know. I'll have to simulate the whole box.
Maybe the AP4400. That's one of them. There's several of them.
So they're just like multiple channels of that.
Mm-hmm.
We actually tried to mux this circuit and it worked horribly.
I think it's ABS 1299.
Okay.
So we'll also look up OpenBCI.
Just a multi-channel EMG.
Multi-channel nearby potential universe.
Did they mux it or use one of these devices?
I use one of those.
Okay. Yeah, because we tried muxing it. It was really weird. We were getting like major channel crosstalk, and we couldn't figure out why. It was like, because we got it to work with a 9-volt first, we created a voltage divider just to confirm that we were using it right, and it worked. There was some small ripple in the DC voltage, but then when we tried to do it with the EMGs, it just fell apart.
There's a fair bit of. You shouldn't get that much though, but I mean, I've used muxes for stuff like this before.
Yeah.
But yeah, look up OpenBCI. Brain computer interface.
Oh, did they do a EEG?
Yeah.
That's
so
cool.
you basically need the same thing.
Yeah. If anything, that's like more complex. If you can make an EEG, it can probably be an EMG, not vice versa.
They're. I mean, they have a lot of hardware to it and a lot to optimize.
Mm-hmm.
Cool. Makes sense.
Yeah. I want to simulate that though, because I still don't like fully.
Sure. Cool deal.
I don't have anything else to do. So.
How's it going, Damon? Could you talk a little louder? Your volume's kind of low.
Yeah.
Okay. So to read them, what are the numbers that are written on them?
Oh, okay. Yeah, it was like 1 microfarad, 10 microfarad,
Okay.
and then 10,000. Yeah, I don't know if that's going.
Say it again. And what?
10,000, like E, 10 for pico.
10,000 E.
E.
So it has 10,000 written on it.
Yeah.
Seems like a large number. Let me pull it up. Not share my screen for a second though. Let's try for the cell phone instead. Okay, so the 10,000 P is 10,000 picofarads, so that's 10 nanofarads. And then you do have a 10 microfarads and a 1 microfarads. So yeah, that's 10 nanofarads or 10,000 picofarads. So if you look at the circuit schematic on the instructables link, where there's 100 nanofarads, you can put the 1 microfarad. So that's in a couple places. And then for this 3.3 mega ohm resistor, you can put one that's 1 order of magnitude smaller. So I think you should have It looks like you have a couple 1 mega ohm resistors. Go ahead and actually put 2 of those in parallel with each other. So it makes approximately 500 kilo ohms. Is that making sense?
Yeah. The 2 of the negatives here, you think?
Say it again.
So you said 2 of the negative ohms?
Yep, go ahead and put them in parallel. And I'll go back to screen sharing. NCP, you can just use NCP 6002. You can ignore it. I'll give you another one. Huh? You'll have to power it. Did the power with the plus or minus voltage? Or then wouldn't that also skew the AC signal? No? It's like, doesn't that VRF act as AC ground? So the AC signal comes from your body, and then it dissipates most of its voltage over this extremely large resistor. But remember, it's going into a high voltage, right? So it gives it discharge path, but the DC current, the AC is more or less might be divided a little bit. Yeah, that's what I'm wondering though, because like if this resistor is way higher than this resistor, then it's going to be a voltage divider. So most of the voltage will be gone by the time. And then it goes into a follower, essentially. Yeah, but it's gone before it goes into that follower, right? Because that resistor occurs in the electrode. It's a simulator test. I want to put a, I'm pretty sure it's 15, so that how bad it is. I see what you're trying to say. Yeah, because with using values such as like 15K and 100K, have you put a buffer acting up with that to see what it does? It should. No, I haven't yet. I'm just treating it as if it follows it ideally, so that like in this invention effect of it there, it'll Yeah, but I need to put a buffer, right?
Yeah.
Pretty sure 15K is actually much bigger than
Really? I'm looking at a paper. It says the skin to electrode impedance is like, I mean, this one says like 200 kiloohms. Yeah, but I read another one that said like 50. So they must be measuring it differently in like times or exactly how they measure. This one used the silver chloride, like 3 whatever.
Any questions, Damon?
Yeah, I'm kind of lost.
Oh, we're at. Hmm?
Did you build use that one program you had to,
Fritzing?
I don't remember the name of it.
That's cool. I got it. So in this design, you actually have 3 amplifiers. then I need another one. So I think. How big's the breadboard you're using, Damon?
It looks about 25 or 30 rows.
I guess I'll try to condense this a little bit. I think I'm keeping it within 20 rows. Is this helping?
Yeah.
Solid. And so one of them goes to the output pin. The other one goes to the inverting node. Yeah, you can. They added it recently. I think it's just some spice thing, yeah. I don't think you need LT spice to do it, though. I don't think so. Could be wrong.
I know in like the top bar, there's like a, you can export it to LT spice.
Now I need to get one connection. I'll just do this. I'm actually going to move the position of this resistor slightly to... Actually, I changed my mind. And so then you can put your LED essentially here. You don't have a small resistor. Oh, bummer. This is going to get kind of tough then. Yeah, I'm kind of feeling Fiesta today. One of those days. Actually, I'm gonna go ahead and use that buffer. Whoopsies. Here, 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 here. You got it, Kareem? You got it?
Oh, yeah,
Oh, you're good. I was talking to Kareem. You're good.
okay.
Now to check my answer to make sure this is right. Hmm? You can just download the zip file in the libraries folder and unzip it. No, it's already, if you download it to the libraries folder and unzip it, now it's in the libraries folder. Yeah.
And then not, instead of doing sketch import zip, every time I do that, if it's like too many folders in the file, I don't know it doesn't.
How many, I guess, folders is there for this one? I do hate when people put their libraries in several folders.
It's like 2, 3.
That's silly. So you should just take out the important part and just put it in the CPP here. What are the other stuff that person has? Okay, so what? I mean, are those the core folder? Is that from Arduino's GitHub directly? I mean, you should be able to tell.
Yeah, it's the before the Arduino core.
So I mean, if it's core, then it's already downloaded. It's already in your. Or you have to. What are you trying to do exactly?
Yeah, I'm trying to get.
What's this? It doesn't. Adafruit have instructions on how to do that.
It does, but they're not super good. And I think what I do is
You should just be able to go to Boards Manager and download all of that. I haven't used that one in particular, but well, otherwise, yeah, you just kind of do what we said before about deleting all the other folders and putting it earlier in the file path. So I think and okay, cool. Still screen sharing.
active electrodes. They have the implementation of it on the
I know some people who have though for EEG.
for EEG. So pretty interesting stuff. You can like get a signal when you're not even touching your body.
Okay. And is it coupling through air?
Talking about it, I think it's made up.
Who's he? Oh, I'm not quite sure that's right.
It doesn't make any sense. No, you guys don't believe me. I'll show you. The employee played you ready? I'll show you how it works. I can't show you.
Mm-hmm. Yeah, the rest of them are just bypass capacitors. Not necessary for this, you can still put them.
Yeah, if you're curious, read the paper Electric Potential Growth. New directions and look something in the body.
Is there gel in between the electrodes and the person? So how far is the electrode away from the person?
It's not a great signal, but they did 30 centimeters.
30 centimeters?
Yeah.
So just send me the paper.
It's not great data.
So the electrode is 30 centimeters away from the person. All right, send it to me.
Caveat, they were in an electrostatically shielded room.
No, that's kind of a big deal, actually. This send it to me. I'll look at it.
I don't think anything's changed it up. It's not 2002.
Yeah. Shocker. If it's in a ESD electrostatically, not a Faraday cage, it's a little different.
I don't know the difference.
How many citations does it have?
197.
Alright, we'll take a look.
They got an ECG signal, but like, it's all the way to pusher. That's the best you can get. That's a good data. Yeah, this was taken at the same exact time.
Did you send it already?
No. I'm doing this all in some PDF. That
Did they mention Did they mention anything about impedance matching?
I read it like a couple weeks ago.
Sure.
The main topic was capacitive coupling.
Yeah, like a positive couple 30 centimeters away from
So cute.
Was it 1970?
I have no idea.
I'm about to say, I'm pretty sure it was like 1700s.
Oh, really?
Yeah, EMG or ECG?
EMG.
Okay, I don't know about EMG, but ECG, he did that forever ago, before Occam's even made. He stuck his foot in a salt water bath, hooked it up to some sort of a. I can show you. It's
People from the 1800s are super inspirational. Like, you look at what they did to accomplish their like science goals.
One sec, Damon. I'll put back the Fritz thing here in a sec.
I think I got it all filled now.
Oh, cool.
So do we, anything else for this to work?
Yeah, power it with a 5 volts on the Arduino and ground here. Mike,
What's up?
you see it? To the right.
Oh, wow. That's some real electrochemical sensing.
Yeah. Just put his hand in the buckets of salt. So, looks like, so this would go to 5 volts to the Arduino. And then this would go to ground. Is there any text anywhere? Well, let me zoom out a little bit and just add the Arduino.
Alright. Check this graph out. This is the control, or the, like a probe, so it's accurate. And then this is the signal that we're able to get.
And don't do ECG from a finger.
An ECG detected at the tip of the right-hand forefinger using a single electrically isolated contact probe.
Interesting. That's signaling, dude. I have to take a look at them.
Yeah, I mean, that was just what they used as a control for timing to see if, like, their peaks matched up. I don't know, check it out and tell me what you think, because I read it and I just didn't really know what to think.
Oh, yeah.
So for R1, since I don't have any resistors, except that are 1 megohm, we'll just put
You don't have any 1 meg ohms in it?
I have 1 megohms, but I don't have 3.3 megohms.
Use 3 of them.
Alright. What about dealing with this?
The bypass capacity?
Yeah.
I'll say it goes in parallel between the whole two, the positive power and ground. So parallel, not series.
Okay.
Since you're here, I'll actually give them to you.
Okay.
I'll actually connect these two.
So what should it be doing?
The LED should blink
Yeah, mine is constantly on.
constantly on.
Yeah.
What capacitor did you use?
The 1 microfarad.
Okay. It's constantly on.
Is it see that I have the songs on it?
Hmm?
The top one have like the songs on the capacitors, which give it away now.
That actually shouldn't matter. You can go ahead and flip it just to see. These are
Okay, yeah, it didn't affect it.
yeah, this is an AC signal, so it shouldn't matter. So you're powering both amplifiers. So this pin 8 is going to positive supply. This pin 4 is going to negative supply.
Yeah.
Then you have one resistor here, 100 kilo ohms, connected to. So this resistor then is connected to the output of the other one behind it. You can go ahead and take a picture and text it to me. That might be a little easier. Can I get a couple different angles, Damon?
Yeah, sorry, pretty good.
Very good. Plug out the power and plug it back in again. Or just disconnect the power connecting to the Arduino, then just plug it back in after 100 milliseconds.
Yeah, still on.
So 1 sec. So the blue wire connecting at the row 1 in your blue rail on the left side. So do you have 2 wires going to ground on the Arduino?
Yeah. Yeah.
That should be fine. Yeah, what's up, Kareem? Just don't use it then. Don't bother using it. Yeah. Yeah, just plug it up, see if it turns on. Power it, see if it turns on. As far as I can see, it looks fine. Where does the green wire that's connected to B19 go? It looks like it's connected to B15. Is that right?
Yeah.
What's at B15?
The 2 resistors there.
So is this, can you see my cursor on the screen?
Yeah.
Is that supposed to be this wire here?
Yeah, I believe so.
So it looks, okay. So is it connected to the same row that's at the 2 resistors and the capacitor?
Yeah. Oh, it would be at the
Does it blink, Kareem? Does it blink? Yeah. Hmm.
Oh, I got it.
Cool.
Yeah, you caught it. That one time.
How fast is it blinking? Can you take a video?
Yeah, I think.
I guess it's somewhere on the order of a second. It's time I start doing trials. Oh, I gotta do one more thing first. Maybe I can try. Ooh, I know what I wanted to try. For the screencast, I wanted to try an online whiteboard app. And I can just use the writing pad on a different computer. And then just screencast off. Ooh, that's going to be messy, but I think it'll work. Hey, look at that. That's cool. Congrats, dude.
We're gonna be using this going forward.
Yeah, I was gonna use it today to like so use it as an interrupt to the Arduino and to display some message. But I guess we're out of time. I would still hold on to it though, since you guys put a lot of effort into building it. So maybe I can think of something to do with it later down the line.
Okay.
Do you have spare components to use, or did you want to keep it put together, or what?
I've got spare components, yeah.
Cool. I'll think of something.
Okay.
Something. Question?
Yeah.
That's probably it from me for today, Damon. Since we're kind of over a little bit, but hope that helps a little bit.
All right. Yeah. Thanks for helping.
No problem. I think next time. So we can't meet. No meeting tomorrow because I have to go to a lab outing of some sort, and no meetings next week either because I'm out of town for a conference. But after that, we'll kind of pick up. Have you been able to do any of the PCB design tutorials?
Not yet. I'm in 3 classes right now. So
Oh yeah, that's a lot. Where are you taking classes?
they're all online.
Oh, got it. Okay, well, I mean, hopefully, maybe next week will be a good catching up time. Otherwise, we'll pick up in 2 weeks from today.
Okay.
All right, cool deal, dude. Till next time.
All right. See you.
All right, have a good one.